In this tutorial, we're going to review using the solver to carry out nonlinear regression. Now, by nonlinear regression, I'm talking about functions that are not linear. And I don't mean linear in the sense of y equals mx plus b. I mean nonlinear in terms of their coefficients. That is, their coefficients do not correlate linearly. So let's open Excel. I've got a couple of spreadsheets that I generated for you. We'll go choose the voltage solver spreadsheet. And let's notice that we have a set of parameters that are defining a function. Right, these are the variables. I've called them here offset. So here's the function. There's an offset for this function. We'll see why. But I've also given you a cheat, which is the actual Excel notation for the formula entry. But notice that we have some XY data here. It's just some voltage variations. We can make a little chart of that. We'll make a scatter with line. We can adjust that later. And we see that there's a sort of a sine function here. Let's get rid of that line after all. I don't like lines. You know that by now. You know that I like black circles if at all possible. So we can adjust. Remember that you have both the fill of the marker and the border of the marker. All right, that looks nice. All right, so what do we do first here? Well, we notice that it's a sine function, and that fits with the model that we've generated. Oh yeah, we can always go back to the design option to change our chart style. All right, so what we need to do first is to generate some model data. So we'll create a new column here, which will include our model data. We'll resize that because it's nice to resize to fit your title. The easiest thing to do today is to just copy this function, and I'll talk about it a little bit as we go, pointing out that each of these absolute references refers to a specific cell, so you have to be very careful to use those string signs in your formula. But notice too, aside from the 5 variables here, notice too that I have not included yet the x values, so we'll have to correct that when we paste it in. For now, just grab it, copy it, drop it into cell B9. You can do that in the formula entry. We'll paste that in. And you'll see that immediately it starts highlighting those guys, but we haven't gotten a line yet on our graph. That's okay, but we have there it is. Once we start entering those values for the function, our model data changes, right? And we see that we generate something that begins to look more and more like our curve. So we have an offset from the 0 of 1, that's our offset. A, or our amplitude, is around 2 maybe. B, the exponential part of that curve, the decay of that curve. Let's give it a 0.2. Looking pretty good now. The omega and the phi, let's set those to 2 and 1 and 1. 1 and 1 looks pretty good. Let's maybe phi can go down to nothing. That's fine. Let's try that for now. So we have some initial parameters, which is very important in a linear regression. We have an initial set of parameters that are pretty good. How are we going to assess the quality of that? We'll look at the sum of the squares of the deviations. So we'll compute how the model and the data deviate from one another in this column that I've labeled here SSD for some reason, and we'll call it E in the function bar equals B9 minus C9, and we get some small number because it's a reasonably good fit already, and we'll autofill that down. Now that's what we've done here is compute the square of the deviation. And we can sum those, so the sum of the squares of the deviation is where SSD is coming from here. We just enter the sum function and the formula bar, sum, and it prompts us, of course, for the range of values that we want to use for that computation, and it generates a number. That's a target. That's going to be our target for optimizing our regression, our nonlinear least squares fit. So we're going to be optimizing that number. We can see that it changes. If we monkey with the parameters and things get worse, then the number gets larger. If we get closer to a good value, the numbers get smaller. So as we'll minimize that using the solver add-in that we generated. So there's various parameters in the solver add-in pop-up menu. The objective is the cell that we're minimizing. So we'll go make sure we've selected B6, and we'll notice that we want to tell it to minimize that value. And we also select the parameters that we're going to vary, and we've given it those initial guesses, very important for it to converge on a good fit. We see that we have a variety of options. We'll just use the standard nonlinear algorithm, and we'll generate a solution. We see that we've already converged on a solution, and we knew that we were close. So we just say OK, and now we see that our variable window is populated with the optimized solutions. Something that's missing from this, of course, is the coefficients for those, but we won't worry about that today. The error for those coefficients, that is to say. But let's look at another example. In this case, I've got a kind of a complex model here. This is a model that describes the chemical denaturation of a protein so that we can measure the stability of that protein to a chemical denaturant. It's a bunch of baselines. We can see that there's this mx plus b popping up all over the place. I don't want you to worry so much about what this is. Just notice that there's some baselines that we have to worry about, some slopes and intercepts, but also we have the crux of the model, which is that the energy and the slope of the free energy of the unfolding is encoded here. Something like that. Got some constants there, RT. Right, so we have a baseline there, we have a baseline there, and a baseline pops up again elsewhere. We don't worry about the derivation of this model today, just to show you that this is a complex nonlinear function. It's also nonlinear in terms of the fit coefficients, or the coefficients as well. So, but we do the same thing. We go here and we generate a column of data. So we have, a column of models. So we have our chemical denaturant concentrations in column A. We have whatever our observables are in column B. I think this happens to be fluorescence, but it doesn't matter. Let's plot those real quick. And we can always tidy this up. So let's play with the range. So if we can right click on the axis, if you can grab the axis, you want to format that axis. And let's change, notice that we can change our axis minimum to 10,000. And our maximum looks okay. And of course, we'd like to get rid of that interpolation. Sure, that's pretty reasonable. And you see that there's an upper baseline and a lower baseline, and this transition in the middle, which is our free energy and the slope of the free energy of the chemical reaction of which protein unfolding is. So, okay, back to our data. We have a data column. Let's generate a model column, and then we'll generate a residuals column, and that's what we'll ultimately minimize. So entering that model is something that you get to do on your own today. Of course, you'll have to enter this manually, whereas I've just copied it from another spreadsheet. You can use mine if you need to, and you'll see that it immediately begins to populate with the contents of our fit parameters, which we have none yet, so it's all going to be zeros. We'll see that, yes, that column is empty. Now we can we can go ahead and populate the residuals column as well. Again, it's going to be empty. we can add the model data to our chart directly by just selecting the chart and dragging the data over to include column C. Nothing appears on our chart, of course. We don't have any data entered for our model parameters, but we can go ahead and start entering those. So our upper slope looks like it's negative and large. Our upper intercept looks to be around 20,000-ish. The lower slope, that last line there, looks pretty flat. Let's give it a slightly positive slope, say 200. Still nothing on our chart. Lower intercept's going to be maybe 10,000. Somewhere around there. Maybe 12,000. Free energy for unfolding of a protein, let's say 5 kilocalories. The slope of that value, maybe 2. Now you see that our model is starting to resemble our data, and we can go compute the sum of the residuals, and we'll try to minimize that. Now you can see that there was a mistake in the way that I was organizing my residuals. I need to make sure I'm referencing the proper numbers, not B2 and C2, of course, but starting with B10 and C10. And we'll autofill. I'd like that to be the square of the residuals. So we can correct that in the formula entry bar. And then we'll drag that down to autofill. And now we should be a little closer to using our solver. All right. So now that we have a cell, B7, that we're going to modify, we can make sure we're happy with our starting parameters. Looking pretty close. And you know that I'm going to want to have the model be present as a line. So I'm going to get rid of the markers and make sure there's just a solid line. Looking pretty good. And now those again are our starting parameters. That's the number we're going to try to minimize. Make sure that we have created the residuals that we want, the square of the residuals. That's looking good. Once your spreadsheet is set up properly, we'll go over to the solver. Again, we'll make sure we set our objective cell properly. We'll tell the solver which parameters we're going to vary. We've unchecked the non-negative values here because at least one of our parameters is negative. That's important. And we'll solve. And in this case, we found a solution easily. And the cells B1 through B7 have been populated with the new values. And there we see the real fit through the data with an estimate of the baselines, slopes and intercepts, but most importantly, the free energy and slope of the free energy of the unfolding.